Thanks. I'm happy so many of you decided to come listen to me. I wasn't supposed to speak at this conference, and then the speaker dropped out. So I got a slot tomorrow, and then a speaker got sick, and actually more sick than what I am right now. So I got their slot instead. What I'm going to talk about today, so my background is Erlang. I've been implementing Erlang systems since 1995. And right now, I'll go in and I'll do things in my sleep almost. And what I've been doing for the last 3 years is writing a book. I don't know how many of you have ever written a book? Okay. Pro tip, if you're going to become a first-time father, make sure you finished it before your first child is born. Because, that's one of the reasons it's taken 3 years. But one of the other reasons is, it's chapter 13. 13 is never a good number. The first 10 chapters were easy to do. I based it on the training material, which I implemented. It tells you how to architect your system. It tells you how to design, on a single node level. It tells you, what processes, behaviors to give your processes. And I put everything into supervision trees. And then chapter 11 started becoming harder. It was about release handling, which, trying to make release handling in Erlang look easy because, the tool chain is not that good. It's there to be hooked into other tool chains. So, and it's really badly documented. So, got that done. And then chapter 12 on software upgrade, incredibly powerful feature in Erlang. Got that done and, worked well, despite it being really badly documented. And then I got to chapter 13. And chapter 13 was completely new. Bodhi was actually really excited by the title. It was originally called Node Architecture. And what I started doing is, what I thought is, how do you architect a single Erlang node? And that's what I thought I was going to write about. And so I start writing. And I continue writing. And then I write a bit more. And then I start thinking about the outage we had once when we were on a customer site, and what we did to avoid making sure that if that particular case happened, avoid that outage. And we just kept on going. And before I knew it, I had probably in excess of 40, 50 pages. And my editor, about 3, 4, 5 months had gone since we'd sent anything to the editor, and the editor was jumping up and down, and he was going, Francesco, what's So I just went in and sent him everything I had, and explained, what I'm trying to do with this chapter is, there's a popular belief that Erlang is scalable by magic. You just use Erlang and everything's going to be scalable, and you use Erlang and everything's going to be reliable. When in fact, a lot of it. It's much easier to write scalable systems, much easier to write reliable systems because of the programming model and because of the semantics of the language. And I was trying to give the guidelines on how your systems would be available and reliable. So I sent everything off to the editor, and he usually responds, reads through the chapter, no matter of length, and responds within a day. And about a week later, I still hadn't heard back. And finally, he does come back to me and starts organizing all of these ideas and all of these experiences, which I was trying to formalize. So I said, I think you need 4 chapters here at least. And that's where we ended up, taking 13 and breaking it up into 4 more chapters. And whilst so I started taking it, breaking it up into chapters, and whilst doing it, I said, okay, why don't we start trying to formalize the way I go in and would design an architecture in an Erlang system. Breaking everything up into 10 easy steps. And I had done that with software upgrade. You try to make software upgrade pretty easy in Erlang, and I managed to break it down into 4 or 5 steps, and the same with release handling. So that's exactly what I did. And in this talk, what I'm going to go is walk you through the different steps I would take when going in and architecting a system. And it doesn't matter if it's a betting exchange, or if it's the backend for a massive multi-use online game, or even a telco system. The concept and the principles are all the same. Highlighting things one should think about. So the first step is, think in terms of distribution. Now, Erlang has built-in distribution in the language. So what you tend to use this distribution for is to have loosely coupled nodes. So a node is an instance of an Erlang virtual machine running. And what you tend to do is split up nodes into node types. I think some people call this microservices these days, or service-oriented architectures, or whatever buzzword happens to be. We've probably been doing it for 20 years. Now, so node types are merely a way for us to describe the overall responsibility of a particular node. So I mean, in this case, I've just taken your typical three-tier architecture, which you use in the web world. The front end is what we call the front end nodes. So all we have here is nodes which are responsible for managing connections towards clients. So it could be a web server, it could be running a REST API, WebSockets, you name it. And they're usually stateless and usually considered unsafe as they're facing internet. We then have what we call logic nodes, and that's where you tend to put all of your business logic. So all of the computation, all of the switching, which deals with your requests. And then we've got a set of nodes called service nodes. Service nodes could be things such as APIs towards third-party services. It could be a database, possibly written in Erlang. It could be just a node which provides a particular type of service for the rest of the system, allowing it to execute. And the goal is the first step in architecting is you need to try to split your system's functionality into manageable standalone nodes. And you do that for a variety of reasons. Instead of having one big monolith, first of all, isolate failure. The second is optimizations. You try to, by isolating and reducing what every node does, it allows you to make sure that your node's either memory bound or CPU bound or IO bound. You split your safe nodes versus your unsafe nodes. In this particular case, the web services, front ends, they're exposed to the internet. You might want to put them behind a firewall and then protect your business logic. Now, once you've split up your system functionality into nodes, and you just need to have a rough idea in doing it, you need to go in and decide what distributed architecture pattern you're going to use. And what comes out of the box with Erlang is the fully meshed architecture. You've got nodes which get connected to each other, and they ended up becoming fully connected. So if you've got 5 nodes in a single cluster, they'll all be connected to each other, which has its pros and cons. It's very easy to do. It's scalable. You can easily write a program to run on a single node and then easily distribute it because of the semantics of the distribution model. The problem there is that you've got limitations. If you've got fully meshed nodes, once you start hitting 50 to 70 nodes, you start getting a lot of redundant connections. And all of these connections monitor each other. They send TikToks when there's no message passing going through. And that starts creating overheads. So that creates a limit, which in the telco space was never an issue. It was only when they started dealing with kind of WhatsApp type of scale, or even machine zone, which is currently running in the back end, the largest playing field with the largest number of users. That's when we started seeing limitations, and we started thinking through and looking at other approaches. And the most common approach is used right now, scaling beyond clusters of 70 nodes or more, is the Dynamo Principle. And that's because, thanks to React, the database, there's a library called React Core, which provides us a lot of the implementations which are described in the Dynamo paper, a lot of the features described in the Dynamo paper. What you do is you've got your key space, and you divide it into a set of partitions, where in this particular example, let me just go on to this slide. What you do is you have a special key. And what you do is you use the Dynamo Principle to redirect your request to a particular node. You go in and you hash the session. It could be a session ID, for example, which you're doing. It could be a unique identifier. You hash it to a particular vnode. Now, a vnode is a virtual node. And what happens is that your Erlang nodes will contain a set of vnodes. In this example, we split our whole key space into 64 vnodes. And by splitting into 64 vnodes, we now go in and find a vnode, which then gets forwarded to that particular node. And using this approach, we now get, we're now able to add and remove nodes dynamically. We're hashing, but the disruption by adding and removing nodes is minimal because it just based, assume we went in and removed node 1, we would have to remove 4 vnodes and move that data across 64, some of the other 64 nodes. It also gives us the ability to have redundancy because we can then copy vnodes across other nodes. So if one node goes down, if one node goes down, we can then access the other node, which is on standby. And the Dynamo Principle in React Core is still very much based on a fully connected network. So the way we start scaling these systems now is using the whole React node, the React Core node, as a switch, as a giant switch, where requests are coming in from the front-end server. They get forwarded to one of the logical nodes, and then from there, they get handled and managed, and then forwarded to another logic node within the whole React Core node, and passed on to one of the service nodes. And so this allows us to start combining different distribution methods and styles. Here's another example which also uses React Core. It's the event store. You might have heard of it. It's a time series database, which uses the React Core as a giant switch, and then it adds all of the nodes as creating a star-like shape. And so it can dynamically scale up and down, managing up to millions of reads per second. So what React Core gives us is consistent hashing. So consistent hashing ensures that when nodes come and go, your whole key space is not rehashed in one go. It gives us virtual nodes, which give us duplication as well. It gives us redundancy, so that data can be copied across nodes. It gives us the gossip protocol, where nodes query each other for the health and well-being. And in case nodes get out of sync, because of network partitions, it will also go in and sync them back into what we call eventual consistency. And finally, we've got hinted handoffs, which is if nodes come back up, data will be moved from one node to another, and sloppy quorums. And I'm not going to go into these details, but it's these are items where, in the space of distributed computing, are almost a must. Another typical architecture is service orchestration, the service bus, considered very enterprisey, I guess, by many, but very popular today. And even there, you could have your service bus, your messaging bus, and then have clusters all along. So you could once again start having clusters with 50, 60 nodes, fully connected, then connected together via service bus. And one of the things to decide on when you're dealing with your distributed architectural pattern is you need to start taking into consideration things such as scalability, availability, and reliability, which are 3 things where your final architecture will consist of a lot of trade-offs in between them. Do you have a system with a static number of nodes? Is that enough? And in most cases, it is. Your typical static system will handle maybe 15, 20 nodes on mid-sized hardware. It will handle 20, 30, 40,000 transactions per second. Another question you need to ask is, do you really need distributed frameworks? Do you really need to add the complexity of React Core? Do you need to scale up and scale down dynamically? Another really cool, distributed architecture, and I've actually not seen this in an Erlang system, but it's basically the peer-to-peer approach, where every node is both client and a server. And they're connected with connections which come and go. And even there, you start using, and this is probably the most scalable architecture of them all, where you start plugging in front-end nodes and service nodes to different parts of the network. Now, once you've decided what distributed pattern you're going to use, the next thing you need to decide is what network protocols are you going to use to let the nodes communicate with each other. Distributed Erlang, well, it comes out of the box, but that's not always the right decision. In this example, assume you've got distributed Erlang, the front-end web servers and your logic nodes running distributed Erlang. Hackers, get access to your front-end servers. They basically get access to these back-end machines. My favorite command is RPC : call, and then you provide the node name, and then OS, which is the OS library, CMD, which is a command, and then RM - RF. And so, someone who maybe likes neat hard drives, would be happy whenever that gets hit that way. So, what you do is you need to make sure that with your web servers, in their backend, you might want to go in and have SSL, for example. You might want to have TCP/IP connectivity, and there are even cases where security is not an issue, but you need to have multiple socket connections because a single port becomes a bottleneck. This is an example. We had an instant messaging server where we were handling tens of thousands of instant messages per second. As soon as we expanded the services, this gateway to handle email as well, a single TCP/IP connection became the bottleneck, and we had to run about half a dozen TCP/IP connections between the nodes because emails, attachments, greatly increased the size. So you basically need to go in and decide, do you use distributed Erlang? Do you use sockets? Distributed Erlang is based on TCP/IP. Do you want to run it over MPI, 0MQ, UDP, SSL? Do you want to have REST APIs between your nodes, AMQP, SNMP? There is no one size fits all, and that's one of the decisions you need to make. And finally, once you've decided your nodes, once you've decided your node types, once you've decided your distributed architectural patterns, you need to go in and define the node interfaces. What functions do these particular nodes export? And usually, the way to do that is using your stories. You start going through your stories and seeing what parts, what nodes types you impact in your request when handling your request. So what you tend to get out of running through the stories is the function, the arguments you need in that particular function, as well as the data which you need locally on that node. And in that way, you start developing your state and your data model. When defining your node interfaces, things to keep in mind is reducing communication. You want to reduce data dependencies. Make sure you've got redundancy as well, and wherever possible, standardized API. So these would be the first 4 steps. Split your system's functionality in manageable standalone node types. Once you've done that, decide the distributed architectural pattern you're going to use. Decide what network protocols your different nodes, node families, and clusters will use. And most of the time, it's a mixture of these. And when you're done, define your node interfaces, the state you'll have in the individual nodes, and your data model. And at this point, you'll have something end-to-end, which works end-to-end. And that's where you start thinking about availability. So availability defines the uptime of a system over a certain period of time. Usually, we refer to highly available systems as systems which have very small downtime, and that will include software upgrade and maintenance included. Now, when you're dealing with availability encompasses actually a large number of terms you need to deal with. The first is fault tolerance. And fault tolerance is the ability of your system to act predictably under failure. And that could mean you're returning an error as well. So assume your client sends a request to your front-end server. That request gets parsed, handled, converted to an Erlang term, and then sent back to a logic node. Now, if your logic node crashes, or your logic node is slow in responding, or if there's a network issue, it could be a large variety of items which go wrong. you get back an error in a timeout, you send back an error to the client. And this is a fault-tolerant system. It acts in a predictable way on the failure. And in this way, in this case, the predictable item is returning an error. And when you get back errors, a predictable action could mean you're going in and looking for other nodes, alternative nodes where you could execute your request. And I'm going to give you an example very soon about that. Now, the second item availability brings to the picture is resilience. So resilience is the ability of a system or a node which has failed to quickly recover. And so, very easy example here, client sends a request, the front end crashes. So the client sends a new request, the front end node has been restarted quickly, or a load balance has been reconfigured, and we're able to handle that particular query. And third is reliability. So when you think about availability, reliability comes into the picture as well. And the reliability of a system is the ability to function under particular predefined conditions. And that includes things such as errors or your data becoming inconsistent. So in this particular case, we go in, we send a request to a front-end server. Once we've sent the request to the front-end server, it might send it to a back-end server. The back-end server, for some reason, doesn't respond. Now, the beauty of dealing with this in Erlang is if something goes wrong with the back-end server, it doesn't matter if it's the process in the node which is terminated or crashed. It doesn't matter if the node is crashed. It doesn't matter if the process or the node is extremely slow at responding, so we time out. It doesn't matter if there's a network partition. What we do is, in between nodes, we handle all of these errors the same. You often get people saying, oh, the network's reliable. Well, it won't be reliable. But we're working to make it even more reliable. That's great, but it won't make your life as an Erlang developer much easier because you still need to handle the cases where network might never go down, at least even if the customer claims so. But the end process might go down. The node might be overloaded and be extremely slow in responding. So you handle all of these errors in exactly the same way, which really simplifies the whole model. But assume a request fails. What happens here is the front-end server now forwards it on to another node. This node responds, and the client gets to reply, completely unoblivious over all of the drama happening behind the scenes. So these are the items you need to think about. So reliability, resilience, and fault tolerance. Now, together with this, you need to start making a decision on how you're going to share your data across nodes. And what you need to do is start thinking in terms of failure when you share your data. You distribute your data to mitigate failure. And that's probably one of the hardest things you tend to do when you're dealing with distributed systems. So once again, your typical example of what I would maybe walk through when architecting a system is, we go in, we send a request to the front-end server. Could be a login request. The login request gets forwarded to a logic node, and we create a session in this logic node, stored in this logic node. Another client goes in. It's directed to this front-end server, which handles and stores the session data in the second node. Now, if this logic node terminates, when a client goes in and it sends a request, it gets back an unknown session. Now, if you're controlling the client, what you would automatically do if your session is not recognized is go in and create a new login. Then all of a sudden, you actually have created a new session on the node which is running. This pretty much equates to sharding. And a share-nothing architecture, where no data, so the share-nothing architecture with no data shared across the nodes. You will have areas where you go in and you share some of the data, but not all of it. And once again, you're doing a trade-off here between reliability and availability here. So assume we go in and decide to start sharing all of the session data across nodes. So if a user logs on, we store his session in this logic node and also in this logic node, but decide not to share the shopping cart. So the user decides to go in and buy a book. He buys a book, and it gets put into this logic node. This logic node terminates when he goes in and decides to buy a train set. His request is forwarded to the standby node, which also has a copy of the session, and the train set gets put into a shopping cart over there. But the two are actually separated. They're two separate shopping carts. You won't go in and copy all of that data. That's another of the trade-offs you need to decide what to do. Because it could, in the case of copying the shopping cart, it's not that expensive, but there might be large volumes of data. Instant messaging, you're handling thousands of messages per second in a single system. You might want to copy the session, but if you lose a node, you might lose the messages going through that particular node at that point in time. But that means that your system will scale much, much more. And finally, the third thing you need to think of is the whole share everything. That's the third approach. And in this particular case, we call this primary replication. You go in, you buy a book, and the book gets stored in both nodes. You lose a node, you buy a train set, it gets stored here, and then node comes back up, you decide to remove the book, and it gets removed from both nodes. And this is basically primary replication, is the way it's called, and it contrasts with primary-secondary replication, where a single primary node is responsible for the data on that particular node. Now, so far so good. One of the biggest problems when you're dealing with distributed data is network partitioning. And the decisions you need to make is how do you want, if you get a network partition, if the nodes are still up, but they're separated from each other. So you get a book in here and a train set in here. When the network comes back up, how do you merge the data back together? And I think in parallel right now, Mark Shapiro is giving a talk on CRDTs, which is one of the approaches we use. So you can have eventually consistent data where the data it tries to merge the data when the nodes come back up. Strong consistency where requests actually fail if you cannot guarantee the consistency of the data. And then you've got everything there in between. And in this particular example, think of the Dynamo paper in Amazon. What happens if you get a network partition? You go in, you delete some items from a shopping cart, which are still in the shopping cart, which you've got, which is in the node you can't access. When a node comes back up, the shopping carts are merged again. So the item you deleted will reappear in your shopping cart. That's how Amazon deals with it. In many cases, you'd end up using a distributed database such as Riak or Cassandra, which does a lot of this for you. But it's, once again, a decision you need to make. And finally, I've been describing all of these functions. And whilst describing these functions, every request has a retry strategy. When you send a request from one node to another, you can either go in and decide, when you send a request, you can go in and have three approaches. One is the at the most once approach. So you send a request to a node, and once you've done, it's just asynchronous, and then you continue executing. So it's almost like a fire and forget. And you've got the risk of this request being lost, because the network might be down, you might be crashing, the node we're handling it might be crashing. But it's usually the fastest and the most scalable of them. The second retry strategy is the at least once. So you need to guarantee that the request executes at least once. And that's when you'd go in and you'd send a request. Let's see, here, for example, we've got at least once. We go in, we send a request. We don't know if this request has actually been executed by the node before the node terminated. All we know is that we didn't get back an acknowledgement. And the reason we didn't get back an acknowledgement could be that this particular node could be extremely busy, so it could still have queued that request, and it might still be processing it, but that request, but we happen to time out. It could be that the request was processed, but that the acknowledgement was lost, that the network went down after it was processed. Or it might not have been processed at all. So what we do is we send it to another logic node, and we continue sending it until one of the nodes actually acknowledges it. And that's the at least once approach, at least once request. And then finally, we have the exactly once. the exactly once request. And those are the requests which we need to guarantee have executed only once. Anyone from Greece here? Okay, I'm Italian, so I'm allowed to joke about Greece. What if you were, Brussels is moving 7 billion euro to Greece as part of a loan. And that you need to make sure happens exactly once. There's a problem there, though. You cannot guarantee it exactly once if you're running everything in a distributed system, because your acknowledgement might be lost, the request might be lost, the request might be received and handled, but you just don't know. And so what happens with these retry strategies with exactly once is it is successful or it has failed. It's either black or white. And if it has failed, you don't know what state you've left your system in. And that's when you need to start triggering. Scripts, or in some cases, even human interaction and intervention, which actually goes in and tries to figure out what happens. And if you're dealing, for example, with money, with stocks, payments, it's an exactly once approach. And something goes wrong, usually the back office goes in and kicks in and starts looking at what's happening. So, writing away, I basically ticked off 5 and 6, where for every interface function in your nodes, you need to pick a retry strategy. So, exactly once, only once, and at least once. And that's for every function. You need to actually go in and trace everything which can go wrong en route, from node to node and from process to process. It's tedious, it takes time, but it has to be done. And finally, for all of your state and data, you need to pick your sharing strategy across nodes. And you do that keeping in mind your retry strategy. Now, all of these choices will have trade-offs involved with them. You all know of the CAP theorem. It's very, very similar principles which are applied to dealing with consistency and availability. So the most consistent approach is the exactly once approach, but it's also the least available because to guarantee consistency, you might have to take your own node offline while someone's trying to figure out what went wrong. At least once becomes more available, but at least once you need to store state and continue sending requests until you get an acknowledgement. So it's consistent and it's available, but there's more risk of failure. And then finally, the most available, probably the least consistent, is at the most once approach, where you fire and forget. So you've got no idea if that SMS or that instant message arrived to its destination. And with consistency, it's exactly the same with reliability. When you're sharing your data, if you share everything, it will be the most available system. You lose a node, you'll have all of your data on this other node. So your users will hopefully not experience any downtime. And then your share something becomes even more reliable, and then share nothing is the most reliable of them all. It's the most available of them all, but the least reliable, because you could lose data, and as a result, when you send the request, you're not getting back the response you're expecting. So you lose a node, you might find an empty shopping cart. And the same applies to scalability. In this case, when you're dealing with scalability, the choices you've just made will have trade-offs between consistency and availability, where at the most once is the most scalable, and only once, is the least scalable, apologies, because you have a lot of guarantees you need to make. It's usually a two-phase commit across nodes, which is not always a good idea, versus the only once. Only once, you fire and forget, and it will become really scalable. It's a fast approach. And the same with availability. The share everything will become the least scalable, the share nothing the most scalable. So, at this point in time, you need to start thinking of the scalability. The choices you've made, how scalable are they? Do they fit your needs? And most of the time, they most likely will. Now, Back in the days, we had big centralized servers. They used to be the bottleneck. We needed more scalability. We'd buy, we wait 1.5 years, we'd buy a faster computer. And the system would run twice as fast. That's not the case anymore. What we're doing now is scaling horizontally. We're throwing commodity hardware at the problem. And that's where, you can read and write on every server, replicate the data, and ensuring that losing a server won't lose any data. So these are the trade-offs you need to think of when you're dealing with scalability. And at this point in time, you might want to go back and actually revisit some of the design choices you made. And you will know, what your throughput of the system is as soon as you start load testing it. And every system should not go into production unless it's been load testing. And there's several types of of kind of stress testing or capacity planning, as I call it, which you should be dealing with. First of all is stress testing. You start increasing the load on your system to find the different breaking points. When do you break your logic nodes? When do you hit bottlenecks in your database? When can your web server not manage it anymore? I mean, there was some great benchmarks over Phoenix, the Elixir framework, where they were handling something in excess of 2 million TCP/IP connections on a single machine. The problem there is great. You've got the connections, but what load can that machine actually withstand? Does it have enough capacity to actually manage a parcel of the requests and then send them to back-end logic nodes? The second part is, so you've got stress testing, you've got load testing, where you run the system close. Once you've discovered your breaking point, you run it close to breaking point to ensure that there's no degradation of service. That after 5 or 6 hours of running it, you don't start experiencing I/O starvation, you don't start experiencing network congestion, and other issues. And then finally, you've got soak testing, where you let your system run for weeks and make sure that you don't get any degradation of service across weeks. Now, out of your stress testing, you should then go in and figure out where to put in your back pressure and your load regulation. Back pressure is when your system's overloaded and starts rejecting requests, versus load regulation, where it tries to even out the peaks and troughs by queuing requests. So assume you've got a third-party API right here, which can handle 30 requests per second. You start throttling these requests, ensuring that that you only send 30 requests down. And so even if your system's handling 60, you will have queued 30 and handle them on a first-come, first-served basis. And this is where you start having things such as, at least in Erlang, you've got ready-made applications such as jobs, safety valve, and another application you can just plug in and start using. And most of the time, the back pressure is handled by the TCP/IP stack itself. It's your biggest challenge when you're stress testing Erlang systems is actually creating enough load on the systems themselves. I think our first experience of going live with a really big, large-scale product, we started stress testing, and first thing which happened is we managed to get the firewalls to crash. So we shut them off. Next thing which happened was we actually got the load balancers to crash. They just couldn't handle the load. The system was running at 30, 40% CPU. We wanted to load it even more. The infrastructure just couldn't handle it. So we removed the load balancers. We got F5s, which at the time were the most powerful ones around. And they were actually able to withstand the load, despite crashing maybe every other day. We get a core dump in the F5s as well. But running, managing, having massive load, is going to be your biggest challenge, ensuring that your infrastructure can handle it. And then finally, when you're dealing with capacity planning, you need to think of your whole no single point of failure. So make sure that, if your network goes down, or you've got a power outage, or you lose a node, or a node is slow at responding, make sure in your end-to-end requests that alternative routes can be taken. You need to think about load regulation, which we covered, and back pressure. And then the final item, which I've not really covered here, is monitoring and preemptive support. Don't think that just because you're running Erlang, your system's going to keep on running day and night. And without any issues. That's not the case. You need to constantly monitor it, and you need to have constant, preemptive support. You've heard about the 9 nines availability, which was, 3 milliseconds of downtime per year. And that's a bit of a myth. But even there, as soon as a node failed, there were scripts which were triggered, which immediately handled and managed the request itself. Is it time soon? Yeah. And so, you need to be very proactive with your preemptive support with any Erlang system. You need to monitor everything which can be monitored. We've had cases where we had hundreds of nodes deployed, and processes were crashing in these nodes. And the only way for us to find out was to actually log onto the nodes, log onto the machine, log onto the nodes, and manually browse the crash reports. And the problem is we weren't even noticing because the processes were crashing and then restarting. You need to start collecting all of this data into one place and make sure that somewhere out there, one client experienced an issue. And so you need to deal with all of these issues one by one. You need to try to monitor trends and monitor spikes and just make sure all of these items are handled. So just to go through, in the end, and I think I finally sent off the final chapter to the editor. These are the 10 steps I managed to narrow it down to. So split your system functionality in manageable standalone nodes. Decide what distributed architectural pattern you're going to use. And note, this is something you need to do very, very early on because it will affect your APIs. It will affect your, your recovery strategies. It will affect how you share your data. It will affect a lot of things. Decide what network protocols your node families, and clusters will use when communicating with each other. This is something you maybe don't need to do immediately, but you need to have a good idea. And so if you're architecting an end-to-end system, you'll know that you might have congestion in certain parts. Define your node interfaces. So exactly what functions does each node respond, and have your state and data models for each particular node. And finally, pick your retry strategy. Is it for every call? Is it at the most once, at least once, or exactly once? You need to go in and for your data and state, pick your sharing strategy across the node, so you know what data and the state you'll have in the individual nodes. From part 4, you now need to decide how you share it, and once you've done that, you need to reiterate through all of your steps, steps 1 through 6, and make sure that what you have actually suits your specification. And this is usually done, in conjunction with load testing, stress testing, and your capacity planning. And at that point, when you're dealing with capacity planning and your stress testing, identify where you need back pressure and load regulation. And there's no point in having a system which handles 10,000 transactions per second when your database or your third-party provider will only handle a fraction of that. So don't over-optimize. Premature optimization is the root of all evil, as Joe says. And then finally, define your operation and maintenance approach. You need to think in terms of alarms, you need to think in terms of logs, and you need to think in terms of metrics. And using these three, for monitoring and preemptive support. Last word of advice: don't over-engineer a system. Even if you're writing the engine for the next generation, massive multi-user online game, or you're building the next WhatsApp, always start small and ensure you get something which is working end-to-end. There's no point in having something which is massively scalable but just doesn't work. Start small and then start expanding. You have your node types. You can always go back and change your distributed architectural patterns once you've gone live. Yeah. Any questions? No? So this is the book. I'm sure you can find it on BitTorrent. And I'm not quite sure. Yeah, exactly. And probably is more up to date than what you get on Safari. But I've basically, Chapter 13 is out. The other ones will soon be released. And if you do like it and use the discount code AUFD for 50% off the digital. And once again, I shouldn't be telling you, but AUFD also will work on all the other O'Reilly titles as well. So they're outside. Don't tell them I told you, but yeah.
Okay. Sorry, if you have questions.
Any questions?
Come up and ask him. Lunch is being served outside, so please.
Okay. I'm around for next 2 days, so yeah, feel free to come up. Thank you.
You can do it right now.